Hello, I welcome you all in this presentation related to the subject fundamentals of the manufacturing processes, and we are talking about the material removal processes. And in the material removal processes we are basically talking about the grinding. So, we know that the milling is a multi-point milling uses the multi-point cutting tool. It also uses like this disc shaped the cutting tool, which will be having the number of cutting edges, cutting teeth like this, and it is engaged with the workpiece for material removal. And if we compare the grinding wheel, we will be having the fine abrasives large in number, and it also performs the cutting when rotating grinding wheel interacts with the workpiece. So, if we compare the two processes, because in both the cases like the rotating tool engages with the workpiece for removing the material, and both are the multi-point cutting, both uses the multi-point cutting tool, but these two differ significantly with the respect to each other in terms of the number of aspects. One is the cutting teeth. This is one. So, the cutting teeth numbers are less in the milling, while in the grinding these are very large number of teeths at any location. So, number of cutting teeths are much more, which will be performing cutting at a time in case of grinding wheel as compared to the case of milling. Normally one cutting teeth performs cutting at a time in case of the milling. So, this is one factor. The second one in terms with regard to the cutting teeth is the orientation of the teeth. So, if we see mostly in case of the milling, milling uses mostly the positive rack angle. So, this is how it is defined as the rack angle for the milling machine, while in case of the grinding wheel it uses the abrasives. So, abrasives are of the different orientations, different sizes, shapes and orientation. So, mostly the orientation of the grinding wheel, orientation of the abrasives in the grinding is such that it offers the negative rack angle during the grinding, and which generally ranges from -30 to -60 degrees. So, when we know that when the positive rack is used, it results in the higher shear angle, it lowers the cutting forces which will be acting onto the tool during the machining, as compared to the case when the grinding is performed. So, the negative rack will be leading to the higher power requirement, more forces which will be acting onto the tooth, means on the abrasives as compared to that of the tooth in case of the milling. So, if we consider the unique volume of the material which is being removed, another one is the speed of the wheel or the milling cutter. So, the milling cutters rotate at much lower speed as compared to what at which the grinding wheels rotate. So, at up to 2000 meter per minute grinding wheel speeds are normally used, but for the milling, like say 300 or 400 kind of the meter per minute speeds or even lower speeds are used. And the third comparative aspect related to the milling and grinding is the self sharpening feature of the grinding wheel. We know that the wear is an integral part of the any kind of the machining process. So, the tool wears out in case of milling gradually, and it needs to be either resharpened or tool is required to be replaced. But in case of the grinding, after becoming dull or after wearing out, the two grinding abrasives break or abrasives fracture, and the fracture of the abrasives after certain time of the grinding operation produces the fresh cutting edges. So, that in turn helps in improving the cutting or the grinding performance. So, this feature is present means self sharpening feature is present with the grinding but not with the milling. So, orientation of the teeth, number of cutting teeth, the speed of the wheel or the milling cutter, and the self sharpening feature. These are the three aspects on the basis of which we can compare the grinding and the milling. If we see the wheels shapes which are used for the grinding purpose, there are a variety of the shapes, like the straight wheel wherein there is a center hole which will be used for the mounting of the wheel. An entire wheel is made of the abrasives, bonding material, and the pores. This kind of the wheel is termed as the straight wheel. Then we have the disc shape wheel, wherein very thin wheel having the one center hole which is used for mainly as a cut of wheel. Then recess wheel, wherein some kind of the gap is obtained in the middle portion of the wheel. So, this is the kind of recess which is given to the wheel. This is the center hole which will be used for mounting of the wheel, and so this is the recess type of the grinding wheel, straight wheel, and the cut off wheel. Then there are metallic wheels, wherein the most of the wheel is made of the metal, like this. Here we have center hole for mounting of the wheel, and near the outer periphery basically abrasives are attached or fitted in case of the metallic wheels. Then we are based on the other shapes like cylindrical wheel. Cylindrical wheel will have the geometry of this kind. This is the central hole, and this is the wheel, and then cup shape wheel will be of like this, wherein there is a central hole for mounting, and the shape of the wheel is of the cup type. Then another wheel is the flare cup shape. Flare cup shape is like this, wherein the center hole at the center. So, this is cylindrical grinding wheel, this is a cup type, and this is flare cup type of the grinding wheel. So, if we see these grinding wheels, like say this is the top view. So, any grinding wheel, a wheel say like this will have certain thickness this manner, and there will be one hole at the center for mounting purpose. So, this is the periphery of the wheel, and this is face of the wheel. So, both periphery as well as the face can be used for the grinding purpose. Like in this case, this periphery of the wheel can be used for the grinding purpose, and when the periphery of the wheel is used, it is called peripheral grinding. Ferrule grinding, and when the face is used, it is called face grinding, similar to that of the milling. If you have to obtain the conditions under which the grinding is being performed, we have to consider the rotational speed and the way by which the wheel engages with the workpiece. Say this is the grinding wheel rotating at certain speed, and in the side view if we see, the wheel is like this, and it is working onto the surface of the workpiece like this. This is the workpiece, and this is the workpiece. So, the rotational movement is given to the grinding wheel. So, it is rotating at the n rpm, rotational revolutions per minute, and this is the diameter of the grinding wheel. Then the wheel surface speed is given using the pi dn. D is the diameter of the wheel, n is the revolution per minute. So, against the rotating grinding wheel, workpiece is fed past the grinding wheel at a certain speed. So, that is what is termed as the work speed. So, wheel speed is say like 1800 to 2000 meter per minute, while the work speed is limited like 20 to 30 meter per minute. The way by which it will be engaging with the workpiece, and the cut is facilitated by moving the workpiece either upward or moving the grinding wheel downward. So, the depth of cut in case of the grinding is termed as in feed, and in order to cover the entire surface area, basically the cross feed is given, so that this will be determining the width of cut. So, width of cut is determined by the W, and the width or in feed or depth of cut is indicated by the letter D. So, if you have to obtain the metal removal rate, then metal removal rate is obtained in terms of the the speed of the workpiece V W, and W is the width of cut and D is the depth of cut. So, the speed at which the workpiece is engaged with the with the grinding wheel, W is the width of cut and D is the depth of cut. So, this is what will be giving us the metal removal rate. So, if you have to obtain the specific energy or specific power consumption for grinding purpose, then the grinding force Fc multiplied by the wheel speed divided by the speed of the workpiece, that is the metal removal rate. Basically, we have to divide the MRR. So, which under the simplified conditions becomes Fc into V. V is basically the pi dn, the rotational speed and the wheel diameter, and V is the W, the speed at which workpiece engages with the wheel, and W is the width of cut and D is the depth of cut. So, this is what will be giving us the joule per mm cube. So, if we calculate the specific energy for the grinding comes out to be extremely high, higher than the conventional machining like milling process. So, we will try to look for what are the reasons behind the high specific energy for the grinding wheel as compared to that of the conventional milling or the machining processes. So, as I have said, specific energy for grinding becomes much higher, about 10 times than the conventional machining like milling process. So, the reason for this, there are three important reasons. One is the size effect, the second is the negative rack of the abrasives which engage with the workpiece for the removal of the material, and third one, that although wheel is rotating, but all abrasives do not remove material, but only few abrasives participate in the material removal process. So, we know that the size effect means what? If the thick chip is removed, then the specific energy is less as compared to the case when the thin chip is removed. This is what we have already learned from the conventional machining itself, because number of in this case shearing needs to be done number of times, and in this case for the same volume shearing needs to be done just once, as well as the number of times the frictional effect which will be experienced will be more in case of the thin chip as compared to the case when thick chip is used. So, in any case when the chip size, the size effect means the chip size is less, then it increases the shearing and the energy required for overcoming the friction in general for given volume of the material. So, the size effect means since the chip size is very fine in case of the grinding as compared to that of the conventional machining, that is why it leads to the much higher energy consumption per unit volume as compared to that of the conventional milling. Another effect is the rack, negative rack. Conventional milling basically uses the positive rack, which helps in increasing the value of the alpha. So, means negative rack means in conventional milling we use the positive rack, alpha is positive rack. So, this as per the merchant theory, the phi, that is the shear plane angle, when the positive rack is used, it increases the 45 plus alpha by 2 minus beta by 2. So, positive rack means it will be giving us the high phi value, and higher value of the shear plane angle results in the smaller shear plane area. So, the lesser forces which will be required as compared to the case when the lower shear plane angle is used. This will be leading to the greater shear plane length, and the shear plane length multiplied by the width of cut will be deciding the shear area. So, when negative rack is used, means the 45 minus alpha, alpha is negative. So, this will be reducing the basically the phi value will be reducing. So, which will be requiring more work to be done for the shearing, and that is why this will be leading to the increased power requirement for the grinding purpose. And all abrasives do not perform cutting. This is a very important aspect related to the grinding, and this is an integral feature of the grinding process itself, which leads to the somewhat reduced removal of the material, as all abrasives do not participate in the grinding process. So, this third aspect that all abrasives do not perform grinding, and the main reason for this is the random arrangement and orientation of the abrasives in the grinding wheel. So, if you see the grinding wheel like this, so the few abrasives are projected more than the other abrasives, and they are oriented in different manner. So, if we see this scenario, maybe 2 abrasives will be performing cutting, and these 2 will not be performing cutting. So, all the abrasives actually here the cut will be performed how? The abrasives will get inside the workpiece, and it will be forming the chip in this form. So, cutting is being performed in this case. For the second case, here abrasive is just penetrating but not performing. So, this will be leading to the elastic deformation of the material, not the plastic deformation, and when it happens, or even if the plastic deformation, shearing is not facilitated. So, in this case when material is getting deformed, but it is not sheared off due to the rounding of the abrasives, then we find an impression on the surface of the workpiece of this kind, wherein the groove is formed, but material is not removed by displacement of the material. So, plastic deformation at the location of the abrasive where it has passed through the surface of the workpiece will be deforming the material or displacing the material sidewise. This is known as ploughing, Plouging, ploughing. So ploughing is kind of the plastic deformation by displacing the material sidewise but not removing it. So the grinding is basically performed in the case when there is a cutting. In ploughing there is no cutting, just displacement of the material, and third stage where abrasive just touches to the surface of the workpiece. So it is performing just rubbing. So depending upon the extent of projection of the abrasives from the surface of the grinding wheel, that determines how the abrasives will be interacting with the workpiece. So based on these three approaches, the abrasives work in three ways. One is cutting, where material is removed; second is ploughing, where material is displaced sidewise, and the third one is just rubbing of the abrasives with the surface of the workpiece. So the ploughing and rubbing basically contributes to generation of frictional heat. So this frictional heat actually affects the surface of the workpiece as well as the grinding wheel. So because of the rubbing and the ploughing, as we have seen, where few abrasives will be performing the cutting while other abrasives will be just causing the ploughing and the rubbing. So that leads to the rise in temperature during the grinding. So rise in temperature during the grinding, especially of the workpiece, if there is a rise in temperature. So if we see the scenario as compared to the conventional machining, in case of the conventional machining, the chips carry away lot of heat being generated in the primary shear deformation zone and the secondary shear deformation zone. So the chips carry most of the heat, while in case of the grinding, the chip size is very small and they are very fragmented. So the heat generated mostly carried by the workpiece. So since most of the heat is retained by the workpiece, as well as part of that will also be retained by the wheel, that is why the workpiece is very badly affected by the heat generated during the grinding. And these effects appear basically in the different forms, which may be in terms of like the cracking of the workpiece, like hardenable steels experience this kind of effect. Apart from this, there can be oxidation, which can lead to the decolorization of the surface of the wheel due to the basically oxidation of the heated metal. And there is one more which is called burning of the material, like formation of the hard spots, and the third one, it can lead to the softening of the surfaces, like the grinding is performed on the heat treated steels. Say it is quenched and then tempered. If tempering has been done at 500 degrees centigrade and for after final heat treatment and processing, if it is subjected to the grinding, so rise in temperature of the material during the grinding, if it goes beyond 500 degrees centigrade, then metal gets over tempered. So over tempering will be simply leading to the softening of the material or softening of the quenched and the tempered steels, or even quenched steels also get softened due to the heat generated during the grinding. And then we have another, but there is one favorable effect of the temperature rise during the machining, during the grinding, is the development of the residual compressive stresses. Since only the surface layers are heated, and when they are heated they will expand, but when they contract during the cooling, this contraction is not permitted because it is metallurgically related. Even if the surface is hardened, it occurs by the martensitic transformation. So both these conditions lead to the development of the residual compressive stresses, and these stresses actually favorable with regard to the improvement in the fatigue life as well as corrosion resistance of the material. So one favorable effect is observed with regard to the development of the residual compressive stresses. And so that was the effect of the temperature rise on the workpiece. Similar to that, the wheel grinding wheel is also affected by the temperature rise as well as the forces. So, like the temperature and the cutting forces are acting on during the grinding, they also affect the wheel, mainly in terms of the removal of material from the wheel. And this happens basically in three ways. Like the wheel is like this, having the abrasives. So, there are three possibilities. One is the abrasives fracture, this is one. Attrition is the another, where the gradual wear of the bond as well as abrasives takes place. And third one is the bond fracture, where in the bond, when bond gets fractured, then abrasives dislodged from the wheel. So, all these three means removal of the material from the wheel through these three approaches, through these mechanisms, lead to the loss of the material from the grinding wheel. So, the grinding wheel, loss of the material from the grinding wheel is also termed as the wheel wear. So, to quantify this, people have developed one ratio which is called grinding ratio. Grinding ratio is basically about the volume of the material removed from workpiece to the volume of the material removed from the grinding wheel, and this indicates that how much material of the workpiece is removed before the wheel as compared to the loss of the material from the grinding wheel. And this may be like the 40 to 100 or 120 ratio is the common, depending upon the kind of work material and the grinding wheel which is being used. So, if you have to see the way by which grinding wheel wears out during the grinding, there are different stages for that, and different mechanisms work in the different stages. And these stages are like so here what we have, the wear of grinding wheel and wear of the workpiece material, or it is basically the volume of the material which is being removed. So, initially when the grinding wheel is placed in use, initially it wears out faster rate, then the wear rate becomes constant, and then it occurs at accelerating rate. So, this one is called break in period, where in initially fresh abrasives fracture, and this is the steady state rate, where primarily attrition, bond fracture takes place, and third one where the abrasives become dull. So, the fracture of the abrasives and the fracture of the bonds takes place. So, here the cuttability in the third phase is reduced significantly. So, without removal of the much of the material from the workpiece, the greater removal of the material from the grinding wheel takes place. So, these are the three stages by which the way these are three stages by the way material loss from the grinding wheel will be taking place. So, here now I will summarize this presentation. In this presentation, I have talked about the specific power consumption related with the grinding and the factors affecting the specific power consumption in the grinding process, and thereafter I have also talked about the way by which the grinding wheel wears out, and how in which way the different phases are experienced by the grinding wheel during its life, in terms of the breaking in stage, attrition stage, and the accelerating wear of the grinding wheel Thank you for your attention.